Welcome to YO Today. I'm Paul Pepis, Director of the Oregon Humanities Center. My guests today are William Phillips and Dave Wineland. William Phillips is a distinguished university and College Park professor of physics at the University of Maryland. He is also a physicist with NIST, the National Institute for Standards and Technology. He was a co-recipient of the 1997 Nobel Prize for Physics for the development of methods to cool and trap atoms with laser light. David Wineland is the Philip H. Knight Distinguished Research Chair and Professor of Physics at the University of Oregon. He's a member of the Oregon Center for Optical, Molecular, and Quantum Science at UO, and he holds a research associate position at NIST and was a staff scientist there from 1975 to 2017. Wineland was a co-recipient of the 2012 Nobel Prize for Physics for the manipulation and measurement of individual quantum systems. On February 21st, 2023, Phillips gave a talk titled Time, Einstein, and the Coolest Stuff in the Universe as a guest of the UO's Department of Physics. Thank you both for coming on the show. It's great to have you with us.
It's pleasure to be here.
So this is a question for both of you. You can fight out who goes first. What sparked your interest in physics? How did you come to that path?
Go ahead, Bill.
Almost as far back as I can remember, I was interested in science. I remember that my parents gave me a microscope when I was probably 5 or 6 years old, and I went around the house looking at everything that there was. As time went on, my interest in science focused more and more on physics. Of course, it was a long time ago, so it's hard to know for sure exactly what it was, but I sort of jokingly say, biology is icky and chemistry is smelly, so physics is the is the thing you go for. Or perhaps more correctly, I have a bad memory. And you have to, at least at that time, you had to memorize a lot of stuff in biology and in chemistry, whereas in physics, all you had to do was remember a few basic principles and you could work everything out. I remember reading a biography of Marie Curie, and boy, that really turned me on. So things like that.
And your story is different. It's a very interesting one, the way you came to it.
Well, even as a young kid, I was interested in math, and my father used to play math games, verbally with me. And so anyway, I was interested in math, and in my senior year of high school, I took my first physics class, and I just thought it was pretty neat how math could explain a lot of the things we see around us. And so actually when I started undergraduate school, I started as a math major, but then I was taking physics as a breadth requirement, but then, that's where I really got interested, so that it's from midway through undergraduate that I knew I was gonna go for physics.
So you're both experimental physicists, right?
Yeah.
So first of all, what's the difference between an experimental physicist and a theoretical physicist? Can you tell me that in a way that I might understand?
We're probably bigger nerds than they are. But
okay, that I get.
I think, it's mainly, as experimentalists, you're dealing with equipment and knowing how it works and how it doesn't work, so you can fix things. And I would say I think in both of our cases we actually do a fair amount of theory in the background, but it's not, it's well-known theory, but we have to do this to kind of verify the experiments. And
so the experiments are meant to test the theory or to modify the theory?
Or just, you're right, Bill. Yeah.
Yeah, or the other way around.
Uh-huh.
Yeah.
We have typically close relationships with theorists. And I see that it works in one of two different ways, sometimes both for the same theorist. One is that the theorist calculates something, and then we go into the lab and see, is that right? Mm-hmm. The other way is we go into the lab and fool around and see something that we don't understand, and go to the theorist and say, can you help us out figuring out what's going on? And it has worked both ways to really good effect.
Interesting. So you've both had long associations with NIST, the National Institute for Standards and Technology. I will be honest with you, I'd never heard of NIST before. So what is NIST and what do they do? What do you do at NIST?
Well, he's at the headquarters, so why don't you start? I'll chime in here.
We are the nation's National Metrology Institute. Every big industrial country has a National Metrology Institute. Why? Because among other things, if you make stuff that has to be exported to another country and it has to meet certain standards, in other words, that something has to be a certain size so that it fits into some other part that somebody else has manufactured, you've got to be able to guarantee that this is really what you say it is. And the ultimate way in which you do that is your National Metrology Institute. So in the old days, people would calibrate their micrometers against NIST standards of length. It was then called the National Bureau of Standards. They would calibrate voltmeters against our standard volts. Now, it's more that we enable people to do those kinds of calibrations themselves, because the modern way of doing things is that standards of length, standards of time are based on constants of nature rather than artifacts. In the old days, a meter was the distance between two scratches on a platinum iridium rod. Today, a meter is the distance that light travels in a certain length of time. And so one of the things we do is provide people with the means to do that.
And it's a government agency.
Yeah.
That's right, yeah. So,
But do you want to add to that?
oh, just stepping back a little bit. I mean, it grew out of the need for, weights and measures, so different countries would be on the same scale, and it gradually evolved. And now, as Bill says, we define things not by artifacts, but by, physics. The speed of light is, it takes so much time to travel what we define as a meter.
One of the legends that is often repeated at NIST about measurement is that around the turn of the century, that is around 1900, there was a big fire, I think in Baltimore, and a bunch of fire departments from different places came in order to fight the fire and couldn't because their connectors wouldn't fit onto, there wasn't a standardization. And so the idea of standardization was an important thing for something as mundane as fighting fires. And that was before the National Bureau of Standards was formed, and is often cited as one of the motivations for creating a National Bureau of Standards.
Oh, that's interesting. So you've sort of given me a sense of how things have changed at NIST over the course of your careers. Can you give us a sense of how experimental physics has changed over the course of your careers, or one or two ideas that will help us to understand that the changes that have happened?
Well, one thing, and Bill and I both share in common, in atomic physics, a big step forward was having lasers that you could tune to whatever frequency you wanted. And both of our experiments take advantage of that. So that's been we would be in the dark ages still if we didn't have lasers. So that was a big advancement.
So they didn't used to have lasers at NIST, but now they depend on them all the time?
Certainly, yeah.
Lasers didn't used to exist. I mean, the laser was invented in 1960, so I was 12 years old then. And it's one thing to have had the first lasers. It's another thing to have lasers that you could use on an everyday basis without being a laser engineer yourself. So the ability to buy a laser that you could then tune so that it would excite a particular atom that you wanted to excite, that started to happen in the 1970s. And there weren't very many different kinds. So when I started, the only thing that I could shine my laser on was sodium atoms. And now we have a huge array of atoms because of the fact that technology has given us these different kinds of lasers. And it's the same for you.
Yeah,
you started out, beryllium was...
Right, so before lasers really became widely available, tunable lasers, the standards of time, for example, were based on low frequency relatively low frequency transitions, and you would count certain number of cycles, that would define a unit of time. And most of the early experiments then were based on radio frequency or microwaves. And in fact, the first experiments demonstrating the laser principle were actually done they're called masers,
Right.
where M stands for microwave. So they were done at low frequency, but the principles are very, very much the same.
And this feature of technology driving science, and then often science driving technology, has been going on for a really long time. Those old standards that actually still represent the official definition of what we mean by a second involve microwaves. Those microwaves were a new technology in the 1940s, mainly because they were developed in order to make radar work during World War II. And it was shortly after the end of World War II that the first atomic clocks came into being using microwaves. And in large part because of the technology that had been developed to make radar work.
That's extremely interesting. I assume there's many such occurrences that are the result of war.
That's true.
Yeah. So first, because you got the Nobel Prize earlier, though I know that you said to me that Dave is senior to you, but tell us about the work you did that earned you made you a co-recipient of the Nobel Prize, and what that was, and what its impact has been.
Okay, so it starts with Dave, in fact. I was a postdoc at MIT. Dave, by that time, was at NBS, at NIST, in Boulder, and I read this paper, 1978. I read this paper in which he did the first laser cooling of a cloud of ions, charged atoms, electrically charged atoms. And I thought, wow. There was this figure. You remember this figure that shows the temperature, and it's going along, and then boom, it goes down to something that's consistent with 0. And I just thought, I want that. I want that for neutral atoms, because that's what I've been working with all my graduate student career, and as a postdoc I've been working with neutral atoms, and I'm thinking, I'm going to do that with neutral atoms. And I started to do that, also inspired by some other papers that I read around the same time, people coming up with ideas, and I think, I can do that. I've got the wherewithal to do that. And shortly after that, I went to NIST, not to do that, interestingly, but to do precision electrical measurements, which was related to other things that I'd done as a graduate student. But they said, you know, since you've been fooling around with this atomic physics stuff, this sounds like something that NIST is interested in. So you can spend a little bit of your time fooling around with that. And 10 years later, it was my whole program.
So tell me about the impact of that research.
Well, so one of the things was that we learned how to take things like cesium atoms. I mentioned cesium because it is still today the atom whereby we define what we mean by a second. A second is a certain number of oscillations of the frequency that corresponds to the energy difference between two energy levels in cesium. Very roughly speaking, it's not perfectly true. It's the difference between the energy level when I've got the nucleus spinning this way and the electron spinning this way, and when the electron is spinning the other way. Okay? A little bit of a lie, but we don't want to go into the truth. Remember, truth and brevity are complementary variables. So, cesium atoms. Normally, atomic clocks were using cesium atoms at a temperature a little bit above room temperature. They're moving along at more than 100 meters per second. It's hard to measure something that's moving at 100 meters per second. And something moving at 100 meters per second has all kinds of shifts in its frequency that you have to deal with. And decades of scientific and engineering expertise had made those atomic clocks good to better than a part in 10 to the 14, but basically hung up because the atoms are going so fast. We learned how to cool cesium atoms down to within 1 microdegree of absolute 0. At that temperature, they're moving at less than 1 centimeter per second. And this has allowed people in Boulder, the atomic clock laboratories in Boulder, to make atomic clocks that are good to a couple of parts in 10 to the 16. And today, many of the industrialized countries all over the world, including, of course, the United States, use atomic clocks that use laser-cooled cesium atoms, based on the kinds of things that we developed in our group.
Fascinating. So Dave, tell us about what your work was that earned you made you a co-recipient of the
Well,
Nobel Prize.
I mean, we were both of our, in fact, I met Bill and we kept a friendship going for a long time because we were doing laser cooling experiments too. And there's one main difference, and it's that we're using charged atom ions, and Bill is using neutral atoms. And so, but there's still a lot of overlapping techniques that we can learn from each other. So that was important. So I would say, when you were talking about the kind of effects we worry about, some of them are really interesting, and there's two that come from Einstein. And what Einstein told us was that, that two reference frames, say us standing in the lab and our cesium atoms going by in a beam. What Einstein taught us is that the frequency in the local frames, on a frame moving with the ions, the frequency is different than the one in the lab. And the fundamental reason is not an environmental effect. What Einstein told us was actually time runs at a different rate in different reference frames. And so that's really interesting. And the second one is his so-called gravitational potential redshift, where clocks, for example, time runs at different rates at different elevations. And this effect now with the best clocks is measured down to the millimeter scale. They can tell this difference for, just raising they have the experiments. I'm thinking of it a little bit more complicated, but they can separate different samples by millimeters and see the difference.
So you're getting to this next thing that I want to talk about, which is quantum computing and quantum physics. So first of all, what is quantum physics? And it doesn't matter to me which of you answers that question.
Well, the trouble with that question
Yes,
is
of course.
that it's loaded with all kinds of background. So on the one hand, quantum physics is everything that has to do with the way in which matter behaves at the microscopic and submicroscopic level that was given to us by the giants of the early part of the 20th century, people like Planck and Einstein and Bohr and Schrödinger and Heisenberg. But today, when people talk about quantum physics, it often means using some of the weirdest aspects of quantum mechanics, which were known to those founders, but which were either not used in a technological way or dismissed as being irrelevant to our real understanding, but are now at the core of new technologies that are taking off. And Dave was one of the pioneers of doing this. Let me tell a story, because I'm not sure Dave is going to blow his horn well enough to hear this, to tell you this story. Those fathers of quantum mechanics often said, quantum mechanics only applies to things that happen on average. The idea of thinking about what happens to a single atom, a single electron, is foolish and should never be considered. We should never think about such things because it'll just lead to ridiculous conclusions. That's what Dave got the Nobel Prize for, was doing those experiments with single atoms.
So you work on quantum computing.
Right.
So tell us something about that.
Well, I mean, this would be people spend semester courses learning things. Yeah. But anyway, so one of the interesting things to talk about is that if you think about memory storage in a classical computer, you have two-state systems, and you label one a 0 and the other level, energy level, a 1. And so that's the way our standard computers work. But in the quantum world, we can reach this strange situation called superposition. So we can make our single qubit, quantum bit, be both in the the 0 state and the 1 state at the same time. And why this gets interesting, if you think about a register of memory of say a standard bits. So if it's if you have n-bit register, you can store one n-bit binary number, and if you have a quantum register, due to the superposition, you can store all the numbers simultaneous from 0 to the largest binary number, binary register. So, go ahead, Bill.
Yeah, and that number is immense.
Mm-hmm.
Let's, when you buy a computer, it may have a terabyte of memory in it.
Mm-hmm.
If you had just 300 qubits, the number of different binary numbers, 300-digit binary numbers that it could store, is greater than the number of protons in the universe.
So how big would a quantum computer be? Would it be massive? I mean, would it be like a supercomputer?
No, not necessarily. I mean, right now, I'd say we're still in the days of making baby quantum computers,
sure.
so we can demonstrate the basic principles. But, controlling things with a large number of qubits, we say, that's the challenge. And so we're still, this is, in part, large engineering problems to control the systems.
So, in theory, once quantum computing is fully realized, it will be able to do calculations far beyond what any computer currently existing could do, much more quickly.
For certain kinds of problems, not for everything. Quantum computers are not particularly great at doing arithmetic. But certain important problems, quantum computers have an advantage, a significant advantage over classical computers. There are some problems, for example, problems in quantum mechanics, where the difficulty of doing the problem grows exponentially with the number of quantum entities. So let's imagine that I wanted to understand magnetism in a solid, and the way I do it is make a model meaning a mathematical description of the thing, where I have a certain number of atoms that are each magnetic and interact with their neighbors, and this is how we understand magnetism. Well, if I have more than a few tens of such atoms, the problem becomes impossible for a classical computer to do, because of this exponential factor, that adding one more atom makes it twice as hard. So when I say exponential, a lot of people, when they say exponential, they simply mean big. What I mean is that the difficulty is an exponential function of that there's a function that's has this form that it doubles when I, or increases by some factor every time I add another. So using a classical computer to do a problem like that is impossible when the problem becomes bigger than a few tens. But a quantum computer could do it. And I think we're right on the verge of doing these kinds of calculations.
One thing people have been excited about in the last few years is, trying to show the strength of quantum computers. And so people have done, various labs have done demonstrations, and they can show for certain types of algorithms or, numerical problems, they can show that the quantum computers all now are much better than a classical computer. And the only trick is that so far these demonstrations have not been done on a useful application. So
how are quantum computers powered?
Well, I mean, in one sense, the computer memory, for example, we don't need any power at all. We just need to preserve the system. Now, in our case, both of our cases, we use lasers to control the states of the quantum bits. But so we usually don't think in terms of cost, at this point. But it's just more on we have enough power to scale up our systems, at least for the near-term future. If we can just get our qubits to behave and not, we talk about decoherence, where they lose their quantumness over a certain amount of time. And those are the things we try to fight against as experimentalists.
Can I ask you a question about lasers that is hard for a layman to get their head around, which is that you've used lasers to cool things.
Yeah.
And we think that lasers are hot. How does that work?
Yeah. Well, he's the one who invented the idea.
Bill did a good job explaining it last night. But No, the idea is there's a couple of simple ideas that come into play, and one is, let's say we have an atom here and a laser beam coming in this direction. Now, if the atom is at rest for all practical purposes, then when we shine the laser on it, the atoms will absorb, say, in a two-level system, they'll absorb the photons when the photons are tuned to a certain precise frequency. And but the other thing we take into account where laser cooling comes in is that if the atoms are moving, then their frame is different than the lasers. So we have to account for that. It's basically the Doppler shift. Mm-hmm. So, but where the cooling comes in is, it turns out if we have rather than assuming if our atom was at rest, we tune the laser to some frequency where the absorption is maximum, but we take care of it. If the atom is moving against the laser beam, the frequency of the laser to the atom will be higher. And so the idea of cooling is that we tune our laser a little bit below where the atom wants to absorb maximally. But if it's moving towards the laser, there'll be some velocity where it's going to absorb maximally. And in this absorption process, we get the momentum of the photon imparted to the atom, and it's a small increment, but by repeating this process many times, we can substantially lower the kinetic energy of the atoms. So.
That's fascinating. So, Dave, you're a member of the Oregon Center for Optical, Molecular, and Quantum Science. Give me a sense of what that center does.
Well, it has a long history in quantum optics, lasers and measurements using lasers. So they have a very strong background in that. And anyway, when I came here, there wasn't really an effort in quantum computing per se. And so, when I came here, to be honest, I didn't want to try to build a big program like there was at NIST. And so, but we were able to hire an assistant professor. That was actually a former postdoc at NIST in Boulder, and so, as I say, or would say, I don't want to build a 30-person group, at my age. And so what I'm doing right now is just trying to help this assistant professor get going, and not that he really needs my help, but anyway, it's fun to interact with his students. So that's what I'm plugging in right now.
So, Bill, I wanted to ask you, can you give us a sense of what your talk was about, like a thumbnail?
Well, it was talking about the basics of laser cooling, just what Dave just described. First, talking about atomic clocks and why the motion of atoms was deleterious to the operation of atomic clocks, why we need atomic clocks, and then using that as a motivation for why we need to do the cooling, then talking about just how that cooling worked and the kind of atomic clocks that we can make today, these clocks that work at a few parts in 10 to the minus 16, and then a little bit about the future, because these clocks that are a part in 10 to the 16, which is incredible, this is just the beginning. Dave has been a pioneer in a different kind of atomic clock, where instead of microwaves, you use optical frequencies. So microwaves, the ones that are used in the atomic clocks, are in the order of 10 to the 10 cycles per second, about 10 billion cycles per second. The kind of clocks that Dave has pioneered is on the order of 10 to the 15, so 100,000 times higher frequency. Now, why is that good? Because if something is messing up the frequency of your atomic clock, like a little bit of a magnetic field or something, then the fractional shift is going to be hugely less if you're working at a really high frequency. And then there's all sorts of other things that make these high frequencies work better. And so Dave's clocks are parts in 10 to the 19.
So what do we use atomic clocks for? What's like some...
One simple example which pervades our world now is the so-called global positioning system. So, when on our cell phones we can find out where we are, and the way this works is, a simple model is, we have this network of satellites, and let's suppose they're all synchronized, so they're all their clocks are running at the same rate. So, by certain protocols, say one of the satellites, and you have a receiver on the ground that will be able to receive these signals. So the navigation system works by, if the clocks are synchronized, then by some protocol we'll say the satellite will emit a pulse of radiation, say on every second tick. And then the clock on the ground, of course, there's a time delay because of the speed of light, traveling, and we measure that time difference. And that's what basically sets the time and the difference of time. And basically it turns out with a network of satellites, have 4 or more, you can not only determine your, I should have said the way that the first part is that, the time it takes for a pulse to get to your receiver is governed by the speed of light. So from the delay time that it takes to reach view, then you compute the length, the distance between that satellite and your clock on the ground. And if you have an array, then you can get length in three dimensions. And that's basically the idea of how our iPhones work.
So if we didn't have atomic clocks, we couldn't know where we were on our iPhone.
Exactly.
We'd still be using paper maps. Yeah, that's fascinating. So both of you have had very long and distinguished careers. What keeps you going?
Curiosity.
Yeah.
I still want to understand more about the way the world works.
One of the things I think about. So we've been working with charged atoms, and so one of the really unique things about the neutral atoms is called Bose-Einstein condensation. And so a lot of the experiments that Bill worked on were building up to do this condensation. And the idea is really strange. If you have 2 atoms, you can make them cold enough that they would coalesce, so-called, and that they condense into a single state, but involves in that case two bits or 2 atoms. But this goes on for many atoms, and this is something people have talked about for many years. And Bill, was pioneering the steps toward doing that. You should cut in.
Well, in order to make such a system, you have to get a gas of atoms dense and cold. And that's one of the things that we had worked on in our group for a long time. We were not the ones who first got Bose-Einstein condensation. A group at Boulder were the first people to get Bose-Einstein condensation, Eric Cornell and Carl Wyman. And later Wolfgang Ketterle, and some time later, we finally did it. But it has been a source of, in a sense, endless new opportunities for research. It seems like every few years, the field of atomic physics and cold atoms reinvents itself with something new coming along. And it's just fantastic.
So on that note, I want to thank you both for joining us. It's been a fascinating conversation. This will go down in history for me as the first interview with 2 Nobel laureates, probably the last. Thanks so much for taking the time. I've really appreciated it.
You're welcome.
It's been a pleasure.
Yeah.
I've been speaking with William Phillips, a distinguished University and College Park professor of physics at the University of Maryland, and David Wineland, the Philip H. Knight Distinguished Research Chair and Professor of Physics at the University of Oregon. Thanks so much for watching.